So moving on to the next part of the theorem, we will show that if you have any two distinct ordinals, one a subset of the other, then it must be an element. Notice that transitivity, in a way, says the reverse, that inclusion implies subset. And so this is going to give us an if and only if in the case of ordinals, and that means that we can kind of freely sort of go in between inclusion and subset in the case of ordinals. This video is just going to be kind of discussing a first collection of intuitions and building a sense of where this proof should be going, and in the next video I'll actually get into the true proof. So one thing to remark, this was just initially confusing to me, is that it didn't seem like it was right that being a subset implies being an element. After all, I could come up with, say, the number 5 and the subset, which is the set of 1, 3, but this is not an element, right? And so how could we explain that, being a subset does not necessarily imply being an element? Well, that's because the set of 1, 3 is not an ordinal, and therefore this theorem does not apply. And therefore, we really must be, using the fact that alpha, the subset, is an ordinal, and something about that must be important for the proof. It's perhaps worth thinking about the various things that are and are not included in the number 5, and in general, when you have an ordinal, it is a transitive set, whereas this so to speak, counterexample or failed counterexample is not transitive. So that seems like maybe that will be an important property of the proof when we get into it. So that's one sort of intuitive remark, is that we really must be using the property of alpha that it is an ordinal. And the next thing to remark is, how do we get this proof started? Well, one thing that, if you think about these ordinals long enough, starts to sound pretty useful, is that these ordinals just are the sets of all things less than them. So if you think of the number 5, for instance, and imagine that you have it as, the inside of, or a subset of, the number 7, whatever. Then 5 is the set of 0 through 4, so it's the set of all things less than it. If you took 7 set minus 5, what do you have left over? You've got the set 5, 6. And the minimum of that is the number 5. If you take the set of all things less than 5, well, that's the set of 0 through 4, and you're back at having the number 5 again. So, in general, it's possibly helpful to characterize these ordinals as being the set of all things less than them, and in particular we need to locate these elements as being drawn out of the set beta, right? In order to establish that this is a set, we need to be clear about where we're drawing, which set we are drawing these things out of, and that would be beta. And we need to have some way of talking about the thing that provides the initial segment, gamma. Well, that would just be the minimum of beta minus alpha. So it's worth having that distinctly in mind. Obviously, I'm about to use it in the proof. I'll go through the proof in the next video.